Hello again, friends. In this video we're going to be trying to find the volume of a shape that's created when you rotate a region around our x-axis. And specifically in this video we're going to be trying to do that using cylindrical shells. So to get us started, I already have a problem written down here for us, and we can see that it says we're going to be trying to find the volume created by this function right here when x equals the square root of y, from y equals 0 to y equals 1. And I already graphed that here for us, so from y equals 0 to y equals 1, and then we see that this is our function that we graphed. That's this guy. And so when we rotate this around our x-axis, that's going to give us the shape that we're trying to find the volume of. So we can see that if we rotate this all the way around down here, that's what he's going to look like, right? And our bounds are the same, so this is -1. So what this looks like, if you think about it, right, we're going to have a flat bottom from our axis, right? It's going from here up to the axis, and then it's going to kind of come out on the x-axis, and it's flat on the sides too, right? So when it comes out on the sides, it's going to be flat because it's restricted with the bounds at y equals 1, and then so it's going to kind of curve around the top here like this. And then what's going to happen on the inside is everything is going to curve into the axis, right? So it's going to be this shape with this kind of cone cut out of the inside of it. So all the way around, we'll see that it kind of curves in and cuts in and creates this cone shape, like a trumpet shape on the inside of our cylinder that we're going to have to remove from finding our volume. So we're going to have to kind of cut that out. So in order to find the volume of this shape, we're going to be using, like I said, cylindrical shells. So in order to do that, we have to use this equation that I've written up here. And it says that the volume of a shape is given by the integral from a to b of 2 pi times a radius times a length, and with this problem we're integrating with respect to y. So what this is kind of telling us is, instead of thinking of like a cylindrical shell, think more so along the lines of the cylindrical surface area. Because what we see is that if we have a cylinder, right, this is our cylinder, this right here is part of the equation to tell us the surface area of a cylinder, right? So you have 2 pi r, so that tells you your radius around the top. Not the radius, excuse me, your circumference, right? This is your radius, my apologies. So this tells you the circumference of the circle that makes up our cylinder. So we have our circumference, and now what we're doing is we're going to multiply that by our length. So that's like the height here of our cylinder. And what this tells us, if we were to like cut along our line here, right, it's just going to be a giant rectangle with a width of 2 pi r and a length of L. So what we're really doing is we're finding the surface area of all of these cylinders in here, so it kind of gets us like the shape of, the reason we're multiplying is because really what you're doing is you're finding the area of a rectangle that's been like curved around, right? So that's why we multiplied the two together. But so what we're doing is we're going to be finding the volume or the surface area kind of all of these like pieces of cylinders that are embedded within our we are going to kind of embed within our shape here, and that when we find the cylinders within the bounds, all of the cylinders, right, there's going to be a cylinder, infinitely many small thin cylinders within our shape. When we integrate within those bounds, what we're going to get is we're going to get the area of the entire, the volume of the entire figure, the entire shape that we're trying to find. So to get us started, kind of explaining how that all works out, I'm going to draw our graph a little bigger here for us, so that way we have a better visual of what we're doing. So let's see. Okay. And then this guy kind of goes like this, and this guy kind of goes like that. I'm actually going to draw that a little bit out further just so that we get a little more space in. So we're going to go more like this. I'm going to go more like there. Okay, and then this is 1, so this is our bounds up here. And then this is our negative 1, and so we're just squeezing the nail along here at the bottom. That's our negative 1 bound. So we've already rotated this around the axis. So now, like what we've done in the past, what we have to do is we're going to, inside our shape here, we're going to put a rectangle, right? Like when we did, whenever we found our area, or when we found our volume using the discs or washer method, right? We always put a rectangle within our shape and given it a width dy. So that's our width, and we've rotated it all the way around our shape, right? So he's going to come over here, and he's going to be all the way around the axis. And we already can see that what that creates is our cylinder on the inside of here, right? It's a little messy, but right, we get our cylinder on the inside of our, we've kind of sliced a cylinder within the volume of our entire shape. So we have a cylinder in there, so now I need to figure out what the radius of the cylinder is and the length of our cylinder is. So our radius, I'm going to fix this first really quickly so that way we can see what's going on a little better. Give me 1 second, friend. There we go. Okay. So the radius, right, goes from our axis out to the edge of our cylinder, right? So our radius is from our axis out to the edge of the cylinder. So what we see is that if we go from our axis to the edge of the cylinder, it's giving us a length along our y-axis, right? And we see that if we were to embed a smaller cylinder within here, so let's see if I can find another color. If I were to have put the rectangle, if this was a rectangle inside here, right, we're going to get a smaller cylinder out of this, because right, he's only going to go to there. So if you rotate him around, just like we did the orange one, we see that our radius has changed, right? So now our radius, we're going from, what do I want to use? Use red. We're going from our, axis, and we're going out to here. Same thing up here. We're starting from our axis and going out to where our function is. So our radius, we can see, changes length throughout our function, right? If we plug in a y value here, that's right here. So let's just say, this was 1, so let's say this is 1/4. Right? If we plug in 1/4, we're going to get a certain spot on our function up here, right? This is our function, so we're going to get a certain value up here. But our value of 1/4 becomes our radius. Similarly, for our big orange cylinder, right, our value, if we plug in, I'm going to say this is 3/4, right, up to here. So this is 3/4. So down here's negative 3/4. So if we plug in 3/4 for our value for our function, right, for our y value that we plug in, we're going to get some x value out here on our function, right, because x is our output. But our input, our y value, that becomes our radius, right? It defines our radius. So whatever y value we plug into our function, that is our radius. So for our radius, what we can do is we're just going to simply replace it with our y values. Right, we're going to go from 0 to 1, so whatever y value we're working at, 0 from 1, that's what we're going to plug in for our radius. Now that we have a radius, we need to figure out what our length is, right? And like our work we did in the past, right, we can see that our length is this distance right here, right? It's the distance of our rectangle that we originally had. This right here. And we see that the length is defined up to our function, right? It's from our y-axis up through whatever our function goes. So down here it's smaller, right? So no matter what y value we plug in, it's the x value that we get spit out from our function, right? So what we're going to do to keep this in terms of y, we're going to fill in our square root of y, right? Because our function defines what our length of our cylinder is going to be throughout the entire thing. So down here, our function creates us a smaller length because we're going from our axis up to our function. Down up here, we have the same thing. We have a longer length for our cylinder because our function goes out, right? It tapers out, and we get from our y-axis to our function gives us a longer length. So what we're going to do, like I said, for our length, we just plug in whatever the function is, since our function defines what our lengths are going to be throughout the entire thing. And last but not least, we have our dy, which we said is the width of our cylinder. So we have a super infinitely small width. And now that we have all of our pieces of our integral, we can begin to integrate and find our volume. So I'm going to erase our picture here. And I'm going to plug in our information that we know. So for this problem, we're going to be integrating within our bounds of y from 0 to 1 of 2 pi. Our radius we said was y, and our length we said is the square root of y dy. That's our integral. Now one thing I forgot to specify or explain before is, right, although we're rotating around the x-axis, like in the past we did, if we rotate around the x-axis, we define our integration in terms of x, right? Here we're doing the opposite. It's defined in terms of y, because what we did, if you remember, is our rectangle, right, is parallel. So whenever we use our cylindrical shells, the rectangle that we embedded within our region, our shape, right, the rectangle is parallel to the axis of rotation. So because it's parallel, right, we're giving it a width, right? It's some infinitely small width, and we're saying because it's along the y-axis now, we're measuring that width in terms of y, so it's going to be dy. So the entire integral then has to be in terms of dy, or not dy, in terms of y, right? Because we're integrating with respect to y. So the axis is the x-axis, so our rectangles, in order to get the cylinder shape, right, that we are looking for, they have to be parallel to the axis of rotation. So that's why, although we're working with rotating around our x-axis in comparison to what we've done in the past, we have to integrate in terms of y now. So now that we have all of that squared away, we can begin our integration. So actually, before we begin our integration, I'm going to simplify this down a little bit, right? So this is the same thing as going from 0 to 1 of 2 pi. I'm actually going to pull my 2 pi out front because he's just going to follow our work all the way through. And we have y times y to the 1/2 gives us a grand total of y to the 3/2, right? dy. So now that we've simplified, we're going to integrate. So we're going to get y. We're going to add 1 to our exponent, so that's going to be 5/2. And then multiply by our reciprocal, so we're going to have 2/5. And then we know our bounds are from 0 to 1. Multiply by our 2 pi. So we plug in 1, we're just going to get 2/5. We plug in 0, we're going to get 0. So we have 2 pi times 2/5. And then you multiply that through, you get a grand total of 4/5 pi. And that is our answer for our volume. That is the volume of this this region, or the shape that we have when we rotated this given region in here. We rotated this region around our x-axis. The shape that we've created, this is the volume of it. And we figured out that volume, like I said, using the cylindrical shell method.